Okay, welcome, Jordan, Ralph, Victor, and Jesus, and hopefully the rest will come also. This is yet another linear algebra day, and let me share my desktop and let's talk about what's going on. Oops, just a minute. Okay, the plan today is I'll start out with any questions that you guys have, as always. And then we'll look at how do you find a matrix to a power. So hopefully you all know that if you want to find a squared, what do you have to do? Not a trick question. So if you have a matrix, A and you want to find the square of that matrix, what do you do?
Square every entry?
That won't work, actually. That would not be.
Multiply by A.
Yeah, so you multiply A by itself. Sounds good, right? So you go A times A. What if you wanted to say A to the 20th power? What would you have to do?
Multiply A 20 times.
So we're going to have fun doing that. Sound good? Maybe it doesn't sound good, but we'll talk about it. We'll talk about avoiding it. So we're going to have strategies for finding A to a power. Okay. And it'll be particularly important, which we won't be doing today, but we'll be doing in a little later, I think on Friday. When you want to do E to the A power. That seems weird, but you know how to do E to the 4th or something. Well, what about E to a matrix? And another day we'll talk about it. So then we'll define what it means, and it's another kind of like rolls off the tongue so well. What does it mean for a matrix to be orthogonally diagonalizable? So we'll talk about that. And then I'll get into the principal axis theorem. And then after that, we're going to do Markov and migration matrices. Okay, we're going to do state vectors and random walks, and those all kind of go together. The idea here is that it's a big application that says if you know the state of something, okay, and that something could be a group of people, it could be an ecological system, all kinds of different applications. And you know what is likely to be on the next step. And each step, you're going to have these movements from place to place. Then how can you use this as a model? And we'll talk about that. We'll finish with random walks. So if you are going from place to place, town to town, and from any particular town, you have a certain percent chance you'll go to the next a different town. Okay, and there might be 5 different towns you can go to, and if you're in one of them, then you can have a probability of any of those 5 towns. And the question is, after maybe 3 moves, where are you going to be, or where are you most likely to be? And that's called a random walk. So that is the plan, and I want to note something. And I hope you guys still agree, but maybe you don't. If we have a review session 2 days before the final, so that's the Wednesday of finals week, and if it's on campus, possibly outside on campus, otherwise in a classroom on campus, depending on the weather, would you come to it? Social distance, mask wearing, all that kind of stuff. Let you know you don't have to worry about me because I've been double vaccinated. I got my 2nd shot. So would you come?
Yes.
Okay. Only 2 people would say yes. Here we go. Now we're getting more. Okay, so because there's a lot of work on my part, and then on the administration part, because they have to go through and get permissions and all, you know how bureaucracy is. So they're doing all this bureaucratic crap and seeing if I could get permission to have a review session on campus. And the idea is I'll live stream it on YouTube so that if anyone can't come or doesn't feel comfortable coming, they can watch on YouTube. So that's, you know, always there. Okay, so that's the idea. And that would be the 24th at 1 o'clock. So that's Wednesday of finals week at 1 o'clock is my thought. And it's optional, and I'm not even sure if it's going to happen or not because there's all kinds of permissions that have to happen. But given the fact that I just got my shot, I'm not a danger to anyone anymore. Okay, at least in 2 weeks officially I won't be, or a week and 5 days. And as long as you wear masks and stuff, you shouldn't be much of a danger to anyone either. So I'm working on it now. I'll let you know when I get the approval from the administration, and then I'll tell you what's going to happen. Sound good? Okay. Are there any questions about anything?
I just have a quick question.
Mm-hmm.
Is it possible to have matrices do the fundamental theorem of calculus?
When you say do the fundamental theorem, a matrix isn't going to prove the fundamental theorem, if that's what you're wondering.
No, not prove it, just use the fundamental theorem of calculus.
So the fundamental theorem of calculus basically says the integral from a to b of f of x dx is equal to capital F of b minus capital F of a. That's the fundamental theorem of calculus. Now, does a matrix do that? No, because that is very abstract. Does that make sense?
Yeah.
Now, if you're asking, can a matrix approximate, especially approximate is a better word than exact, a definite integral? Is that what you mean?
Kind of, yeah.
So if the question is, can a matrix approximate a definite integral to as many decimal places as you want? The answer is yes, as long as the function is nth differentiable, where we're looking at an n by n matrix, and you do it with power series. If you're wondering.
I was, yeah, that's curious.
You do it with power series, and the power series can be done by matrices also. You still have to be able to evaluate a function. You know, otherwise you can't do anything. But if you can evaluate the function, then you can actually use matrices to do that. It can't prove the fundamental theorem of calculus, but again, you can approximate a definite integral for sure to as many decimal places as you'd like.
That's cool.
Okay, and indefinite to as many to as high a power of power series that you want. If that makes any sense to you. So the answer is, I think yes, but not quite the way you said it.
Sounds good to me.
Yeah. Okay. Other questions? Could be homework questions.
Yeah, can we go over problem number 7, please?
Okay. So number 7. Let me go find it. You know how it is. Always takes a little extra time. Just a minute. Just a minute. That's 7.2, number 7. Just a minute. There it is. Just a minute. I got to move all the Zoom stuff. I know you can't see what I'm doing, but trust me, I'm getting the Zoom stuff moved. Oh, shoot. That didn't work. Just a minute. Let's get that guy up. just a minute. Sorry, that didn't work. One more try. Just a second. One more try. And that one. Got it. Always takes a while to do the copying a page and put it into the Word. Okay, so here's number 7. This is the one you want, right? So suppose that A is an n by n matrix. What a surprise. And let V be an eigenvector such that AV equals lambda V. Also suppose the characteristic polynomial of A is determinant of xi minus A equals this beautiful polynomial. So using x instead of lambda. Explain why a to the n plus am minus 1, a to the n minus 1, v equals 0 is dot. So we have to explain that. And then if A is diagonalizable, give a proof of the Cayley-Hamilton theorem based on this. And the theorem says A satisfies its characteristic equation. Okay. So we have to explain why if you plug in A into the polynomial, you're going to get 0. Okay. Do you have an idea how to start?
Plug in A.
What's that?
We can plug in A.
Yeah, well, it's kind of already plugged in because we have this a to the n, a n minus 1, a to the n minus 1 plus dot 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 plus a1a plus a naught I v, and we're trying to get 0. That's the idea. We have to get equals 0. So maybe I'll write down, probably the best way to do it is I'll write down the left-hand side. And that is a to the n, and then plus a sub n minus 1. One more time. A to the n minus 1. Plus dot 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 plus a1 a plus a naught I, and and then times v. So I need some parentheses. And I need to get 0 when I'm done, right? So what do I do? Any thoughts?
Distribute out V, maybe?
Yeah. Except distribute through V, right? Out's the opposite direction. So we're going to go equals. And let me copy and paste so I don't have to type it again. Let me almost. So now we're going to have times V, and then times V, and then times V, then times V. Any questions so far? Okay, then what can we do? The hint is, what is V? V is a special vector. It's not any vector. It's an eigenvector. Yeah, because it's an eigenvector. What is, for example, AV?
It's lambda V.
What's A squared V? Remember, A squared V is A times AV.
A times lambda V.
Right, but what's A times lambda V? Because that's lambda times AV.
Lambda square V.
Oh, it would be lambda squared. Yeah.
Good, good. So A squared V is lambda squared V. What's lambda? What is A cubed V?
Lambda cubed.
Yeah, lambda cubed V, right? So now let me write in words, since V is an eigenvector, we know AV equals lambda V. So A squared V equals A times AV equals A lambda V equals, oops, that V should be in capital, equals lambda AV equals lambda squared V. And I'm just going to write by induction. In other words, I could do this again and again and again. That's what induction basically is. I'm not going to give all the details, but hopefully you can see. So by induction, A to the K V equals lambda to the KV. Any questions on that? So hence, now what I can do is I can take this and we know that A to the NV is lambda to the NV. So I can take that A and replace it with lambda. And similarly, this A to the n minus 1 becomes a lambda to the n minus 1. And this A is just a lambda. And we got that, right? Anyone lost on what we just did? Getting pretty, right? All right, what can I do now? The hint is undo the first step. That's the hint. So what can I do now?
Factor out V.
Yeah, now I could factor out the V. So to do that, I guess I should have equals on all these. So factor out a V, so the V's are going to be moved to the outside. All right. But now, what's lambda to the n plus am minus 1, lambda to the n minus 1 plus dot 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 plus a1 lambda plus a naught I. No more I anyway. We factored out the V. And what is that? In one easy way of writing,
0.
it's 0, because we know that lambda is a solution to the characteristic polynomial equals 0, right? So because of that, you get 0 times V, And I hope you all know what 0 times v is. What is it?
0.
0.
0.
Well, the 0 vector, right?
Yeah. Yeah. Kind of the way I do things in class. I say 0, and whatever context makes sense is the context we're using. So the 0 vector in this case. And that's it. Any questions on why it is that A satisfies the characteristic polynomial? Okay, so then if A is diagonalizable, give a proof of the Cayley-Hamilton theorem based on this. This theorem says A satisfies the characteristic equation. Okay, A to the n plus dot 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 plus A naught I equals 0. All right. All right, so we know that A is diagonalizable, right? So what does that tell you?
That it has a number of eigenvalues that's equal to, well, it has a number of eigenvectors that's equal to the dimension.
We know that. That's true. I don't know if that's going to help, though, but it is true. We want to show that, because remember, we don't want a vector, we want a matrix at the end, right? But the idea here is that now what we can do is choose the basis of eigenvalues. I say eigenvectors. Any questions on that? So we can choose the basis of eigenvectors. Well, if you choose the basis of eigenvectors, then what is A? So we're going to just change the basis, and we can do that, right? So we're going to write A. We're going to say, what is A? And we're going to think of A now as a linear transformation. But now we're going to look at the linear transformation with respect to the basis of eigenvectors. So because of that, what does A do? In particular, in what's the shape or what's the type of matrix A that we get? It starts with a D.
A diagonalized.
Yeah, not ized, but
A diagonal matrix.
right. Then with respect to this basis, the linear transformation is a diagonal matrix. Let's call it D. Sound good? So I just changed it to the diagonal matrix D. So now we're thinking of it as linear transformation. Remember, matrices and linear transformations are the same thing, as just thinking of them in different ways. Okay? As long as we're talking about what we know today, which will be changed in a couple weeks. Okay? Any questions so far? All right, well, once we have that, once it's diagonal, then what does a diagonal matrix do to a vector? Or we can think about what is the power of a diagonal matrix, and it's going to come up today, actually. What is a power of a diagonal matrix? So for example, so I'm going to spend a little extra time on this because this is what we're talking about today. So for example, let's say A, let me give you a good old matrix. Let's do a 3x3, just because 3x3s are hard to take powers of, but we'll be able to do it. Let's suppose we have 2, 0, 0, 0, 3, 0. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, -1. And let's say we take that to the 4th power. What do you get? The hint is it's really easy. Kind of what this is what today is all about.
You take the things along the diagonals and take them to the 4th power.
Right. You don't have to do any multiplication at all, matrix multiplication. So that's going to be 2 to the 4th is 16. 3 to the 4th is 81. And -1 to the 4th is 1. Is that clear? All right. So what that tells us is if we plug in our D into the characteristic polynomial, then all it's doing is it's treating the diagonal entries, which happen to be eigenvalues, individually. So in other words, a to the n, let's write it in a matrix equation. So a to the n, let's go a to the k. I could say d to the k, actually. Actually, I do want, let's see, I want a to the n. Let me get this right. D to the n, and then plus an minus 1 times d to the n minus 1 plus ... plus a1 d plus a naught I guess I got to go times I. So that's what we're looking at, right? We're plugging in our D now because now we're looking at linear transformation with respect to this nice basis. Well, what that is now is if we look at the, let me write that down this way, has 0 along for all non-diagonal entries. And that's because if you take D to a power, you always get zeros off the diagonal. And I also has zeros off the diagonal. And the characteristic polynomial and the characteristic polynomial with the eigenvalue plugged in for each of the diagonal elements. Any questions on that? And that's it. Because now we know that if you plug that in, you get 0. Now, if under some different basis, you get 0 for all vectors, what do you know about it under the standard basis? So if you have a linear transformation under some weird basis and you always get 0, what do you know about in the standard basis?
It's I.
Definitely not I. So if the matrix is the 0 matrix, if the matrix is a zero matrix under a strange basis, what is a matrix? What is that? What is the matrix in a standard basis?
It will be 0 as well.
It'll still be zero, because zero matrix times anything is always a zero matrix. So therefore, A satisfies the equation. Any questions on this idea? And that's the proof of the Cayley-Hamilton theorem. All right, you should complain because look, it took two famous mathematicians to prove it, and I asked you to do it by yourself. But you did have me to help. Any questions at all on question number, what number are we on? 7. Okay, no questions. Any other questions that aren't too long? If not, I'm going to move on. Okay, so let's move on. All right, so here's, imagine being asked to find a to the 100th, or maybe even a to the 10th, but let's call it a to the 100th by hand. And a is 7, -2, 0, -2, 6, -2, 0, -2, 5. Okay, maybe this is a test question. And I say, what is a to the 100th? What would you do?
Lie down and cry.
Right. Well, that's better than what I wouldn't want you to do, which is cheat. Use a computer or something and, cheat and not do it by hand. Okay, so at the point now, you would lie down and cry. How about on the second exam? Do you think you'd lie down and cry?
Probably not, because you're going to teach us how to do it today.
Exactly. So what we're going to look at is we're going to say we don't have to lie down and cry. We can take a to the 100th, okay, and we can do this in probably 5 minutes, okay. And you just have to use what we've learned how to do already. Okay, and you kind of set this up with the homework question that you guys just asked. Because if you notice on the homework question you just asked, we talked about taking powers of a matrix. Do you see that? And we're going to kind of use that idea to come up with something like a to the 100th. And we'll be able to do that, and we'll be able to do it, and we'll have a nice, pretty answer. I mean, pretty is eye of the beholder, of course, but it won't be so, miserable that you'd lie down and cry, I don't think, right? Unless you didn't study for the test, and then you're going to lie down and cry on every problem, okay? But given the fact that you've been practicing everything, we're going to be able to take a to a power, like a to the 100th. And by the way, do you think it's important to be able to take a to a big power? Think that happens ever? In the real world? And not day-to-day life, that never happens. But engineering world or physics world?
Absolutely.
Yes, absolutely. And we're going to have some examples today. We'll have more examples later. You'll get more next quarter. It turns out taking a large power of a matrix turns out to be really important. So that for now, you'll have to trust me on that. It's not just some kind of, math exercise I'm giving you, but actually you do want to be able to take powers. And one of the main applications is e to the a. And do you remember what e to the x is?
Power series?
Yeah, do you remember the power series for it? Good.
No.
It's the summation of x to the n over n factorial. Does that ring a bell at all? Okay, so e to the a will be the summation of a to the n over n factorial. So if you want to be able to handle an e to the a, you have to be able to take a to the n. And you have to be able to get a nice formula for that. And you certainly don't want to do it by hand, right? Because then you lie down and cry. Instead, we're going to have a nice way of doing it. And it turns out, and this you won't get till next quarter, you want to find e to the a because you're going to solve the differential equation y prime equals ky, where y is a matrix. And that you did, you've seen that before, but not with matrices. And you're going to be doing that next quarter to solve systems of differential equations. And trust me on that. It won't be me, it'll be Bruce, because he's teaching next quarter that class. But you'll have to do that. So just let you know, this comes up in a big way. It's not just, a mean exercise I'm giving you. This is one of the main applications of linear algebra. So we want to be able to take a matrix like this, and we want to be able to say, well, how do we get a large power of A? Now, do you notice anything nice about this matrix? What do you see?
It almost wants to be triangular.
All right, wants to be triangular. That's not yeah, but it isn't triangular. If it was triangular, it would be nice, but it's not. There's something else, something specific about it.
Linearly independent.
I don't know. Are you able to do that just by looking?
No.
I don't know if that's true, actually. I'm trying to remember. I think that's false, actually. Might be true, but I have to remember. I wrote this example. I don't remember whether it was true or false.
At least
It's close to being diagonal. I mean, that's kind of similar to the close to being triangular, but
Okay, it's not diagonal. It's not triangular. It starts with an S.
It's a square matrix.
Starts with an S. You remember? I know we haven't used this word in a long time in this class, but we did use it. We defined it. Remember? Symmetric. Do you remember that word? That was, if you take the transpose, what do you get?
The same.
Yeah, you get the same. So notice A equals A transpose. Okay, and that's actually important, it turns out. That's not obvious at all right now, but you should be able to look at this and say we have a symmetric matrix. Okay, at least that's something, right? And it turns out that's what you want. Okay, that's much more important than diagonal, actually. Okay, now if it's already then triangular, not diagonal. Diagonal is easy, but if it's triangular, there's still a lot to do. But if it's symmetric, it turns out we're going to be able to answer it. So any questions on our goal for today to be able to do something like this? Okay, so now we can start writing down some theorems that are going to help us solve our goal. So the first one is the following. Let's suppose that we have diagonalized the matrix A. So we have to make sure that if we have a diagonalizable matrix and we diagonalize the matrix, that means A is equal to PD P inverse. Then to take a power of A to the K is equal to P D to the K P inverse. Okay, and that's not immediately obvious because you'd think, wait, that's not how you don't get to choose only one of them to take a power of K, right? Seems like I made a mistake, doesn't it? Because
Yeah, it's a little strange.
yeah, but we'll prove it and then it won't be strange anymore. So let's prove it. Okay, I'm going to prove by induction. Sound good? So first thing, proof by induction. Induction is a really important method of proof. And whenever you're trying to do something for some integer value, that's usually induction. I do want to note something, and I hope this doesn't confuse you too much. The book uses n for the powers. I like to use k. I don't think the book made a good choice because n is A is an n by n matrix, and this works for any power, not just the dimension of the space. So just let you know, I think the book doesn't use a good letter. So if you read the book, you'll see n, and it really should be k. It'd be better. Okay. All right. So proof by induction for k equals 1, or for n equals 1, I guess. Sorry, k equals 1. Why is it immediate? Why is it just obvious?
Well, it's just one, so P inverse.
Yeah, you just plug in 1. What's A to the 1?
A,
And what's D to the 1?
D.
There's the theorem for 1. So hopefully that was obvious to everyone, was it? So it's obvious. Okay, so now assume that it's true for K. Do you remember how induction works? What do we have to do? Do you remember how mathematical induction works?
Well, we just did it for the homework problem. Like if it works for one example, then it will work for all of them, right?
No, mathematical induction, which is not proof by example, but induction. So you say, assume it works for K, and what do we have to prove? Do you remember? Yeah, K plus 1. Then, and now let's do the K plus 1. So A to the K plus 1 I hope you all know this, is A to the K times A. Y'all agree with that? Kind of by definition, really. All right, but that, again, we're assuming it works for K, so that means A to the K is P D to the K P inverse. And A is P D P inverse. Any questions on the plugging in? Okay, what can I do now? What do you
You can group P inverse with P.
Right, what's P inverse times P?
It's I.
Yeah, so that's equal to P D to the K I D P inverse. What's ID?
It's just D.
Yeah, so P D to the K times D P inverse. But what's D to the K times D?
That's D to the K plus 1.
Yep, D to the K plus 1. Times P inverse. And that's it, I'm done. That's our goal. We proved it that if it works for K, then it works for K plus 1, and that's done by mathematical induction. Any questions on the proof? So it's a nice, pretty proof. So that's why, I try not to do proofs that take, an hour long, but if it takes less than 5 minutes, I'll go for it. It's kind of my way. Any questions on this thought? Okay, why is this important for our idea for this evil question that I originally gave you, let's find a to the 100th. Why is that going to help us?
Because we just prove what a to the k is.
We know a to the 100th is p times d to the 100th times p inverse, right? D to the 100th, we saw on that example, the question you guys asked, d to the 100th is easy. You just take the 100th power of every number in d. Does that make sense? And then we multiply by p and p inverse. By the way, what's the hard part about this whole thing now that we have this theorem? What do you think?
We need to find d.
Okay, so there's actually two hard parts. One is finding d is definitely a hard part. And what's the other thing that might be hard? Might be a little bit of pain.
Find p.
Well, once you found d, p is easy, right? In other words, if you find the eigenvalues and eigenvectors, then you got p, right? But once you have p, what do you have to find next?
P inverse.
You have to find p inverse. By the way, is it easy to find the inverse of a matrix?
No.
It's kind of a pain, right? Okay, that's something hopefully you wouldn't lie down and cry if I asked you to find an inverse. But if you could avoid it, you'd avoid it, wouldn't you?
Yes.
On the other hand, if we can get p to be very nice, then we'll be able to get p inverse to be nice also. We'll get p inverse to be really easy. Now, do you remember what kind of matrix had really easy inverses? Starts with an O.
Orthogonal.
Yeah. So if we can get P to be an orthogonal matrix, we're in really good shape. Is that clear? Because then you don't even have to, and then to find P inverse, you just find its transpose. And I don't think any of you would sit down and cry when I asked you to find a transpose of a matrix, right? Then the smile should come on your face instead of the tears, right? If I said, find the transpose of this matrix, and it was a 3 by 3, that's like nothing. So let me give you this definition.
Do you mind going back up to that last theorem real quick?
This one right here. Okay.
Ah.
Yeah. So if A equals PD P inverse, then A to the K is P D to the K P inverse. So it makes A to the K much easier. But we can even get a little easier, which we'll see in a bit.
Awesome. Thank you.
Can I scroll down a little now?
Yeah, go ahead.
Okay. So here's a definition. And again, I don't know, maybe I'm just weird, but I love saying it. A is called orthogonally diagonalizable. It almost sounds like a song, doesn't it? Orthogonally diagonalizable. If A is equal to P D P inverse, where P is an orthogonal matrix. Okay, so if it's and the key is that if P is an orthogonal matrix, P inverse is really easy to find. Do y'all agree? So that's a big definition. Okay, not too much to say. It's just a definition. But now comes an important theorem, which is going to help us in the question that I asked you. And this is the following are equivalent. I didn't write TFAE because I don't want you to get confused with the big TFAE. This is kind of a little minor TFAE, but it's going to be used today. And that is, the first is A is symmetric. Okay, do you remember what symmetric means? I've already talked about it today.
The transposes are the same?
Yeah, A equals A transpose. Okay, so if A is equal to A transpose, then A has an orthonormal set of eigenvectors. And if A has an orthonormal set of eigenvectors, then A is orthogonally diagonalizable. And by the way, if A is orthogonally diagonalizable, then A is symmetric. Any questions on this theorem? Any questions on this? Okay, this is a theorem I'm not going to prove. I think it would take like a week of work just to prove this theorem for you guys, and we don't have that time. Okay, it's not in the book either. The book says this is too hard for the class. So even the book won't prove it. And if the book doesn't prove it, then this is way too hard. But it is provable, just not in this class. But do you believe it? Hopefully you do. Why does 2 apply 3 immediately? That if A has an orthonormal set of eigenvectors, then A is orthogonally diagonalizable. Why is that obvious?
Because that's the definition of orthogonally diagonalizable.
Basically, yeah. Because remember, if it's orthogonal, if it's diagonalizable, then the P is equal to the matrix whose columns are the eigenvectors. And if the columns are orthonormal, then we've orthogonally diagonalized it. So 2 and 3 are obviously together. The symmetric gives you 2 or 3. That's hard. Do you trust me on that? One that it's hard and the other that it's true, that it works, that it's actually a theorem. Okay, so any symmetric matrix is orthogonally diagonalizable. That's the main thing. Any questions on this theorem? Okay, well, with the theorem, I can go back and now I can answer this and not have to lie down and cry. What do I do? If I want to find a to the 100th, what should I do? What's my first step? And the hint is it's not multiply a times a.
Find eigenvalues.
Yeah, the first step is to find the eigenvalues, okay? Because we're not going to start multiplying a by itself over and over and over again until we start crying. Instead, we find the eigenvalues. And I hope you remember how to do that. Do y'all remember how to do that? I think I'm going to let you try it. I think it's good. I think it's good for you to practice in class. And then I'll look at it after and tell me what the eigenvalues are. Get a paper and pencil out. It's going to take a few steps. And by the way, the hint is they're nice. They're not going to be some miserable, with horrible square roots and stuff like that. I picked a good one. As long as I don't have any typos, and I don't think I do. So should take about probably 3 minutes, maybe less. This is where having the 0 helps a little bit because the determinant's a little easier. And if you have questions, you can ask. But hopefully, especially if you've been doing your homework, you know how to find eigenvalues now. I know you've been doing your homework. I should say, if you've been paying attention while you're doing the homework, it's a better way. So let me ask you what you get for the eigenvalues. Maybe I'll write the first step. Hopefully you all did that. That's an easy step. Uh-oh, you got some messy numbers. If I don't have any typos, they're not supposed to be messy, but maybe I should double check my work while you're working. -2, 0, 7, 6, 5, and a bunch of -2s. Oh, there might be a mistake. Ah, you know what? I apologize. That's why I'm checking my work. That's why you're having troubles. That negative shouldn't be there. I apologize. Let me do it then. Sorry about that. There was a typo. Then it's easy. Okay, but you still do a minus lambda I. And then I'm gonna go along the first column because there's a 0 there. So that's equal to, sorry about the typo. Here, there it is. So it's going to be 7 minus lambda. And then it'll be times 6 minus lambda, 5 minus lambda. And then minus 4. And then we'll have a plus 2 times, and now find that minor, we get -2 times 5 minus lambda. So we killed that one, and we killed that one. And minus 0, so just that. Any questions on that? And it's a bit messy. It's a bit messy, but we can get this work done if we need to. But maybe I'm going to jump to the chase, since I wasted your time by having a typo. And I will let you know that the eigenvalues are 3, 6, 9. Any questions on that? Okay, let's find the eigenvectors. How do we get the first eigenvector?
Plugged in our eigenvalues into lambda.
Yeah, we plug in the eigenvalues into lambda. So now what I'm going to do is I'm going to grab that matrix. And now we're going to plug the first one in. How about 3? 7 minus 3 is 4. 6 minus 3 is 3. Immediately, these are not multiples of each other. So that means the bottom row just becomes 0 when you are REF. Any questions on that? Now I can, I don't know, how about double the second row added to the first row? And when I do that, the 4 becomes a 0. 6 plus negative 2 is 4. And negative 2 times 2 plus 0 is negative 4. Any questions on that? Okay, we're getting there. Okay, so the good news is I kind of done just about what I need for now. Because what do I know about the free, what's the free variable? Just by looking at this.
C is a free variable.
Z is a free variable. So for now, I'm going to let Z equal 1. Well, if Z is 1, what is Y? That should be easy. Look at the first row. That's the hint.
It will be
-1.
Not -1, but
4.
not 4. The hint is we've got 4y minus 4z equals 0. And z is 1. This isn't hard, I promise. What should y be?
Oh, it just be 1.
Y is 1. Because 4 times 1 minus 4 times 1 is 0. Okay, well, if z is 1 and y is 1, then we can say negative 2x plus 3 minus 2 equals 0. Is that clear to everyone? So what's x?
It's 1/2.
Yep, 1/2. So our vector here is, we can write 1/2, comma, 1, comma 1, but that's not the one I want. Remember, how many eigenvectors are there that correspond to the eigenvalue 3?
Oh, linear.
How
Should
many?
be 3.
No, that correspond to the eigenvalue 3. How many vectors are there?
Oh,
There are
1.
infinitely,
Not one.
infinite,
There's an
infinite.
infinite number of vectors. Okay, but what I do know, since the eigenspace has dimension 1, I do know they're all multiples of this vector. Is that clear? Any questions on that? So they're all multiples of this vector. What's going to be which one do I want?
Probably let's see it equal to.
No, you're forgetting about what the big theorem we had a little while ago.
The one that's going to make it orthogonal.
Basis.
Yeah, so I want it to be orthogonal. I want an orthogonal matrix. So what does that mean? What vector do I want? How do I get an orthogonal matrix if that's going to be one of our columns? What do I have to do this 1/2, 1, 1?
Multiply it by 1 over the magnitude.
Yeah, I got to multiply by 1 over the magnitude. Now the magnitude of this is 1 plus 1 plus 1 plus a fourth, right? Which is 9/4, right? Times take a square root of that. And the square root of 9/4 is 3/2. So I actually need to multiply by 2/3 because I divide by 3/2. So the one I want, so the eigen vector that I want is 1/3, comma 2/3, comma 2/3. Any questions on how I got that? Any questions? Okay, I think I don't want to waste your time, but if I asked you to, could you find the orthogonal, okay, or in this case, the unit length, the unit vector that is an eigenvector for the eigenvalue 6? Could you find that if you needed to?
Yes.
Good. And is it okay if I just tell you what it is instead of doing all the messy work?
I'm cool with that.
Okay. So 2/3, 2/3, one that. So we've got that. And the idea here is they're all going to be kind of nice. Let's see if I can get these in the right order. 3, 6, 9. Then we had, here we go. 1/3, 2/3. 2/3 the first, negative 2/3, negative 1/3, 2/3. So and let me write eigenvalue that I want for eigenvector 3 is that. And now let's do copy and paste so I don't have to type it over and over again. So the eigenvalue that I want for eigenvector, sorry, that should be value. For eigenvalue 6 is going to be negative 2/3, negative 1/3, 2/3. And the eigenvector that I want for eigenvalue 9 is 2/3, negative 2/3, 1/3. Any questions on the point of doing this? Okay. And then you could check, it's always good to double check that the magnitudes are all 1, but you can see they are, hopefully. Okay, so now I can rewrite my matrix, and let's write down this matrix again. That's our A. Is equal to, well, now I can write down as our P, and our P, if you remember, is the matrix of eigenvectors. So 1/3, 2/3, 2/3, and then negative 2/3, and then negative 1/3, and then 2/3, and then 2/3, and then negative 2/3, and 1/3. Any question that that's our P? Okay, and then we do our D. So it's diagonal, which means that's a 0. 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 What should this first entry be?
3,
3. What should the second be?
6.
Good, which happened to be there already. And then 9. Now I need to find P inverse. And why can I do this like in my sleep?
Because it's symmetric.
It's the
It's-
original is
it's
symmetric.
So you just have to take the transpose.
Yeah, I just take the transpose. So I take the transpose of this matrix. So the transpose will switch the negatives here. These stay the same actually, and these get switched. And that's my transpose. Is that like the easiest inverse you've ever seen? Okay, so it's if you happen to have a symmetric matrix and you orthogonally diagonalize it, this is very easy. Okay, then if I wonder if I can get rid of some of this. Yeah, I need space. So I want a to the 100. So to get a to the 100, the idea here is I can use a theorem that says, what do I do now?
Yes, d to the 100, p d to the 100, p inverse.
Right, and d to the 100 is really easy because that's just 3 to the 100th, 6 to the 100th, 9 to the 100th. Any questions on that? Okay, and I'm not sure if I'm going to waste your time watching me do this, but do you all know how to multiply matrices if you need to? I hope so. So then
Yeah,
you-
but for one like this, would we probably be given a calculator? Like, not have to do it by hand, the matrix multiplication, I mean.
Well, I certainly wouldn't ask you to find 9 to the 100th by hand. But the point is that you can do it symbolically pretty easy. Matrix multiplication is not hard at all. Maybe I'll do it for you. Since you want to be given a calculator, I want to show you that this is nothing. Okay, or it's pretty easy.
It's just that's a lot of fractions, so it's kind of scaring me initially. Like thinking about doing dot products with all that.
Yeah, but they're pretty easy because take a look. If I do the dot product of this column with this row, that's just 1/3 times 3 to the 100th.
Oh, yeah, because they're zero. Okay.
So even that's easy. So we're going to have 1/3 times 3 to the 100th. Then the next one will be 2/3 times 6 to the 100th. You know, I'm certainly 6 to the 100th is not a nice number to work out, but if we leave it like that, it's not bad. Then 2/3 times 9 to the 100th. And then the next one will be 2/3 times 3 to the 100th. And the next one will be -1/3 times 6 to the 100th. And the next one will be -2/3 times 9 to the 100th. Okay, the next one will be 2/3 times 3 to the 100th. So you notice it's basically just, you take the number and multiply by whatever it is to the 100th. And then the next one will be 2/3 times 6 to the 100th. And the final one will be 1/3 times 9 to the 100th. Okay, now the next one's a little messy, but you could do it if you had to, right? But imagine trying to take the original matrix to the 100th without this theory. Do you know how evil that would be? Do you all agree? Okay, even if you let a computer do it, imagine doing this like in some kind of, fantasy, computer game that's, and some kind of real-time animation, and it's going to have to compute that. No one will want to play that game because they're going to have to wait 5 seconds for it to do the computation. So when you're building a game like that or doing something with computers, you often want to have the most efficient way of solving the problem. If you have a less efficient way, then it just chugs. So being efficient is important, actually, even with computers. Any questions on that? Especially when there's animation involved. All right, I think I'm going to move on. And now comes the next application. Okay, and this is more of a real, real life application. And here's a definition. A is called a Markov matrix, also called a migration matrix. If A has only non-negative entries, and if the sum of the entries of each column is 1. So that means the summation I equals 1 to n of aij equals 1 for every j. So if all of these are true, I mean, if that's what we have for every column, then we call it a Markov matrix or a migration matrix. If the sum of numbers is 1 and they're all positive, anyone know where that comes in a lot? And here's a hint. It's the other class I teach, not linear algebra.
Statistics?
Yeah, but it's the other word in the name of the class. No one uses it, but you know the word. Probability. Because if you have the list of your probabilities, they have to add up to 1. Do y'all agree? All the probabilities have to add to 1. And you can't have a negative probability. Is that clear? So this is the big application. And it comes up all over the place. Any questions on the definition of a Markov or a migration matrix? Okay. So here's how it's used. If a population size remains fixed. So imagine, let's suppose the following. You have the United States of America. Okay. And we're only going to look at the 50 states. Otherwise, it's too complicated. And we're going to assume nobody dies, nobody lives, nobody dies, nobody's born. Okay, we're in some weird world. And there's no immigration, and nobody leaves the country either. Got it? So you got like super border walls. Okay, you're not even allowed to travel. Okay, but you can travel from one state to another. That you can do. Then you can say there's 50 different places a person could be, right? You could be in California, you could be in Nevada, you could be in Arizona. I can go on and on, right? Okay, so then you wait a year and you look and you say, well, people are allowed to travel in the United States. They just can't leave the United States. Got it? Or die. Okay, so the idea here, and no births, no immigration. Okay. So the idea is that the matrix A, this Markov matrix, is going to give the probability to move from one place to another, or from one state to another. So in this case, in my example, it'd be a 50 by 50 matrix. Can you imagine that? So for example, let's say the first column represented California. Then the first number might be 0.6. That would mean after a year, you have a 60% chance of still being in California. Maybe the second one would be Nevada, and that first column, second row might be, say, 0.1, and that would mean you have a 10% chance of being in Nevada after 1 year. Does that make sense? And you can go through every state and calculate the different probabilities. So the matrix A gives the probabilities to move from one place to another. Anyone lost on what I'm talking about? Okay, so if V naught is a vector of counts of how many are in each location now, so we take a vector V naught, and in this case we're going to have 50 different numbers, right? We're going to have the population right now today of California. And that might be, I don't know where we are, maybe, what are we, 40 million? I have no idea. Okay, and that will be the first entry of our vector V naught. And then our second might be Nevada, and that might be 2 million. And that'd be our second entry of the vector V naught. And the second entry would be Arizona, and that would be whatever that number is. Okay, so V naught is a vector that counts how many are in each location now. V1 is equal to A V naught. So if you take A, you multiply by V naught, you get V1, which would be a year from now, how many people are in each state. Any questions so far? So that's the counts of how many will be in each location after one period. After K period, so if you want to say 12 years from now, then VK is A to the K V naught. Any questions on this idea?
So what you're saying makes sense, but I thought probabilities were integrals.
Okay, so I'm not going to get into it. Probabilities are integrals for what's called continuous distributions. So that's when you have a whole continuity of states that someone can be in. So that would be if they wanted to find out the longitude of the person. With the state, there's only 50 states. There's only 50 places you can be in. Longitude is an infinite number, right? Exact longitude. Does that make sense?
Yeah, definitely. Thank you.
Okay. Now you can get more advanced and you can realize this can be written as integral. I'm just not doing that. That's graduate level math. So it's easier to just call it this way because you don't have to be a graduate student or someone with that knowledge. So after k periods, vk equals a to the kv naught is called the kth state vector, and that's that'll be the distribution of how many people are in each state after k years in my example. And vk plus 1 is equal to a times vk. Because if you know after 11 years how many are in each state, and you want to find out after 12 years how much are in each state, then you just take a times the vector for 11. Do you see that? Okay, this is a major application. Okay, I know it's kind of abstract. It's like, doesn't sound like an application. Trust me, it is. Okay, there are a lot of times where you do have this, even though I put in all kinds of just assume nobody has children. I mean, of course they have children, but there's a lot of other applications where this works. Any questions on this? Okay, so here's an example of what's called a random walk. Okay, suppose there are 3 locations. Okay, because the last thing I want to do is type out a 50 by 50 matrix. Do y'all agree? You don't want to do it. You don't want to see it. Okay, but do you think you'd ever deal with 50 by 50 matrices for this kind of stuff?
Yeah, probably.
Yeah, and do you think you'd write it out?
No.
Absolutely not. Absolutely not. You'd use a spreadsheet program and you'd program the computer to do it. Got it? But if you don't understand the ideas, then you're worthless. Because you can sit there at a computer, and if you don't understand what's going on, it won't help. You and the computer can't work together if you don't know what's going on. Okay, you just don't have to do the tedious stuff. So I'm not going to do the tedious stuff. I'm going to say, let's suppose there's just 3 locations. Okay, so now we can think of it as, I don't know, California, Nevada, and Arizona, and that's all there is. Got it? Okay, so the first thing is this right here, is this a Markov matrix? I want you to look at it and tell me.
Yes. All the columns add to 1.
Yeah, so you need 2 things. One, all the columns add to 1. Okay, and that's actually the harder one. What's the easier thing you also have to look at?
Square.
Not at negative entries.
Yeah, no negative numbers. No negative numbers. And I hope you can just look at this and say there's no negative numbers. Can you all see that? Yeah. Yeah, square is also something you need, but we didn't talk about that. But yeah, you do want a square matrix. So you need to make sure only positive entries, and they all have to add to 1, and 0.4 plus 0.5 plus 0.1. Hopefully you can, in your sleep, say that's 1. 0.3 plus 0.2 plus 0.5 is 1. 0.7 plus 0.1 plus 0.2 is 1. Okay, so if we could kind of think about this as my California, Nevada, New Mexico example, then that would tell you that if you started in California, there's a 40% chance in a year that you'll still be in California. There's a 50% chance that you'll have moved to Nevada. And there's a 10% chance that you'll have moved to Arizona. Any questions on that? Whereas if you started in Nevada, there's a 30% chance you'll move to California in a year. There's a 20% chance you're going to stay in Nevada. And there's a 50% chance you're going to move to Arizona in a year. And if you started in Arizona, there's a 70% chance you're going to move to California. There's a 10% chance you're going to move to Nevada. And there's a 20% chance you're going to stay in Arizona. Any questions on that? Is that clear? Okay, so the first question I have, and I have a few to do, even though I only wrote 1 here. If a traveler starts in location 2, so let's say they start in Nevada, which is I'll call location 2, find the probability that she will be in location 1 after 3 years. How do we do that? Any thoughts? So what's the process to find out the probability she'll be in location
Should we
1?
find the probability that she will be in that location in one time period?
Good, good. Yeah. So the first thing is you find the probability that she'll be in location 1. Okay. And actually 1, 2, and 3, not just 1. Okay. And what we're going to do is the way you find that, because this is how Markov or random walk Markov matrices work, is the following. Is you take your matrix A and you multiply it by your vector V naught in this case. Now, if the traveler starts in location 2, we could think of it as there are 0 people in location 1, there is 1 person in location 2, and there are 0 people in location 3. Is that clear? And what's that equal to? How do we, hopefully you all know how to multiply these?
Point 0.8. Well, 0.8 in the 0.
It's a vector, not a number, it's a vector.
0.
So it's a vector. So we're going to multiply. We're going to take the first row, 0.4, 0.3, 0.7, dotted with 0, 1, 0. And that just gives you 0.3. Then you're going to take 0, 1, 0, dotted with 0.5, 0.2, 0.1, and that gives you 0.2. Then you're going to take 0, 1, 0, dotted with 0.1, 0.5, 0.2, and it gives you 0.5. Any questions on that? Okay, are we done?
No.
No, why not?
Don't we have to do it 2 more times?
Yeah, we just found out after 1 year, we haven't found out after 3. So let's do it again. So now I need to not multiply by 0, 1, 0 anymore. I need to multiply by 0.3, 0.2, and 0.5. Okay, now it's a little more work, but it's not that bad. So you get what? 12. I'm gonna multiply by 100 and then divide at the end. So I get 12 plus 6 is 18 plus 35 is 0.53. Any questions on that? Okay, then I go 0.5 times 0.3. So basically, I'll ignore the points and do them at the end. 15 plus 4 is 19 plus 15. Let's say 15 plus 4 is 19 plus 5 is 24. Okay, and then I do for the third row in this column, I get 3 plus 10 is 13 plus 10 more is 23. By the way, how do I check that I might have done it right? What's a good little check?
Add them
Yeah, and what should they add to?
to 100.
Huh? Something very easy. They should add a 1. These are probabilities, right? Remember that she's not allowed to leave California, Nevada, and New Mexico. In Arizona. So she's going to be in one of those 3 places, 100% chance of being one of them. Add them up, you get 1, and it does work. Any questions on that? Okay, that's year 2 now, right? Now let's do year 3. So we're going to do the same idea. I don't know if I can do it in my head anymore, but I might be able to. We'll see. Okay, so yeah, 53 times 4 is 212. 212 and 72 is 284. 284 and 161 is 445, if I did it right. And let's do the other one. 53 times 5 is 265, and 48 is 313, and 23 is 336. Okay, and then we do 53 plus 120 is 173, plus 46 is 219. Okay, should never trust me when I do this really hard stuff in my head. Yeah, you could use a calculator if you need to, but figured I'd drop it in my head. And there's our answer. So that means that if she starts in location 2, which I called Nevada, then there is a 44.5% chance that she'll have moved to California. If you look at her in year 3, there's a 33.6% chance that she'll be in Nevada after 3 years. And there's a 21.9% chance that she will have moved to Arizona after 3 years. Any questions? Any questions on this idea? Any questions? Okay. It doesn't feel like it has that many applications, and I did some kind of fictitious thing, but it has a lot of applications. Where else could this be applied to? Now let's go to science. Where do you think this could be applied to?
I was thinking like chemical reaction.
Definitely chemistry. Okay. So now if you're looking at chemistry and you now have maybe, 3 different chemical compounds, okay, and especially in nuclear chemistry, by the way. So, and there could be a nuclear reaction, and especially if you look at interstellar nuclear reactions, where it could go in either direction because there's enough energy, then you can say, well, if you wait after 1 million years, how much iron, how much, calcium, how much oxygen, how much hydrogen is there going to be after a certain amount of time? Okay, any questions on that? Okay, so that's a biggie in chemistry. And in particular, one of the things you often want to do is say, well, we don't really care about a cubed, right? The third period. We really want to look at 1 billion years from now. We want to look at a very large value of k. So what is the limit as k goes to infinity of a to the k times our vector v?
Wouldn't it be 1?
Well, it's a vector for one thing. Vectors can't be 1. They have 3 numbers, right? Or however many numbers you've got. Whatever the periodic table, I don't know. You probably know how many elements are there in the periodic table, how many there are there. So if you know, and you're doing some modeling of, let's say, some kind of solar system, okay, or a galaxy, and you want to find out, well, if we wait another 1 billion years, how much of each element are you going to have? So in the universe time, so if we look, after 1 billion years after the Big Bang, after 5 billion years after the Big Bang, after 100 billion years after the Big Bang, how much of each element are you going to have? This is how you do it, is you do a model using a random walk or Markov chain. Any questions on that idea? So that's definitely one example of how you use this. Okay, and that would be chemistry slash physics. I never quite understand what chemistry is and what physics. What's the difference between chemistry and physics? Maybe you can tell me, because they go together. You can't have one without the other. So chemistry, physics, call it that. What else might it come up?
Population growth.
Yeah, definitely population growth. Okay, and whether it's human or animals or plants, because you can do the same thing as you can look at ecosystems. And in an ecosystem, you can say, you know, given the fact that there's a fixed amount of sunlight, for example, which is pretty much true, is that, you know, a year from now, we're going to have the same amount of sunlight as we have this year. Okay. That you're only going to have so much energy to, you know, feed all these plants and animals. Then each year, what are you going to see for the next one? And then the next year, and the next year, and the next year. Okay. Where else might it come up? So it comes up all over the place.
Economics.
Yeah, econ for sure. So then you're looking at all kinds of things. Well, you might look at, you know, how about our economic system in America, you know, taxes and stuff. And you say taxes go to certain places. Well, the idea is that if you spend more money in taxes on the homeless, well, you're going to have fewer homeless, and then you don't need to spend as much money on the homeless, right? Okay. But then maybe you're going to spend more on wars. I don't know. I'm just making things up. The point is that you have a fixed amount of money that you're going to spend money on to for all the different things you have to spend it on. And then each year you're going to have to, you know, retax. And depending on what you did the year before, you're going to have probabilities of what you need to do the next year, and the next year, and the next year. Okay. Or for businesses, same idea. Okay. So what I want to mention is that this has like pretty much every kind of thing you can imagine. This is important. Game theory is another one. And any of you know game theory?
You mean like counting cards?
Okay. Not quite counting. No, counting cards is not game theory, actually.
Like that's
Or
stuff like mutually assured destruction, right? The people who like came up with that whole concept.
Yeah, I was going to give you a little happier one than you gave me.
Okay.
I was going to say poker. But yeah, you could do mutually assured destruction too. But I was going to go for poker because it's a little happier. And the idea is that you have a hand. So each time the matrix happens is when the hand happens. Now you're going to change a strategy by watching what they did on that hand. So if someone bluffs, you're going to say, aha, now they have a higher probability of bluffing. If someone doesn't bluff, they have a lower probability of bluffing. Does that make sense? So each time you play the game, you're going to apply this matrix to get different probabilities. And then pretty soon, you're going to be able to make decisions better than you were able to make before. Okay, based on the different kind of things they can do. And it's not always bluff versus not bluff. There's different things people can do. I'm not going to get into the details of poker, but I used to teach a class on mathematics of poker. So we're about out of time. We're going to do more of this next time, by the way. So I want to let you know, I just want to give you hints on some of the stuff that can come up. So let me stop my share. And I'm going to stop the recording.
Would this also be used in